Welcome to this lecture about hands-on introduction to OpenMP. First of all, I'd like to acknowledge that I have taken a lot of inspiration from slides that have been developed by Intel sources. Also, I will refer to some exercises. You can download the source code for these exercises from the course website. Go to the KTH social site for this course, and you'll find a link where you can download these things. So this is the outline of the entire presentation. I will not go through all of it in these slides, but some of it, at least about these things, all right? We begin with an introduction. So this could be seen as an overview of OpenMP. It's sort of a subset of all the directives that can be used for Fortran or for C, C++, and so on. So this is sort of showing an example of the API for writing multi-threaded applications. It's a set of compiler directives and library routines to make parallel programming a little bit easier than using explicit threading. It actually greatly simplifies writing multi-threaded programs in Fortran, C, and C++, and standardizes the last 20 years of shared memory multiprocessing practice. Some basic definitions here. Okay, so I will show you now how OpenMP sits sort of in the hardware system software stack. So at the bottom we assume that we have a machine which have a number of processors or cores in a multi-core processor. These processors share memory address space, or have a shared address space. On top of that sits the operating system and a runtime library where OpenMP, supporting OpenMP programs. And then on top of that, we have directives which guides the compiler into how to compile OpenMP programs. There's a library for OpenMP programs, and the whole execution is governed by the use of environment variables. And then you have the application. And it's shown like this because the end user can control how the application runs by changing environment variables, and that will change the behavior, how the application interacts with the OpenMP library in particular. So all or most, at least, constructs in OpenMP are compiler directives. So in C or C++, they look like hash, pragma, followed by the keyword OMP. So all OpenMP pragmas or directives have the keyword OMP. And then you have the name of a construct, and each construct then can be made to do different things by means of clauses. So one example here is the pragma OMP parallel directive seen here. Pragma OMP, as it always started, parallel tells that the next compound statement will be executed in parallel by a team of threads, and num threads tells that the number of threads to be created is 4 in this case. If you're using library routines, you need to include this header file so that you get access to them. And most OpenMP constructs apply to a structured block, which is one or more statements with one point of entry at the top and one point of exit at the bottom. You cannot have the beginning of the structured block at the same line as the directive. This is not possible. It has to begin on the next line because the pragma is not part of the C program or C++ program. It's the directive that modifies the compilation of the next structured block. You have to tell the compiler to use OpenMP. So if you're using GCC and you want to have some optimization, maybe level 3, and then you tell it by specifying F OpenMP, and then whatever you want to compile after that. This will enable OpenMP support in GCC. If you're using the Intel compiler, which has keyword ICC, the same thing can be achieved by writing -OpenMP. So the same thing except the F. So we have now the very first exercise you could do, the hello world program, just to verify that your environment works. Oh, by the way, I should go back here and tell. If you're using another compiler than GCC or ICC with command line options, you may need to look in the manual on how to enable OpenMP. All compilers have OpenMP. Bear in mind, the Microsoft compiler included in Visual Studio is not does not implement the latest standard of OpenMP. For the very latest update, use GCC or Intel's ICC. Okay, back to the Hello World program to verify that your program environment works. So we have here a main program with two print statements, one printing hello and an ID of a thread, it's the meaning, and the other one printing world. And as I said, for different compilers, you compile with different switches. GCC minus F OpenMP, ICC minus OpenMP. If you have downloaded the Oracle C compiler, it's CC minus X OpenMP. So different things for different compilers. And this is the code you need to write to make this run in parallel. Pragma OMP parallel. And then you have beginning of the compound statement here and the end of the compound statement here. And now I think the idea was that we should print the ID of the thread, and then you call a library routine, and to get access of library routines you include the omp.h, and here you call the function omp get thread num. Okay? This is written here. Okay? So we have the OpenMP include file. We have the parallel region. This is this part of the program. Okay? We're using now the default number of threads. We did not specify the number of threads to create here. We'll talk about how we do that later on. And we call a runtime library function that gets the ID of the thread. So when we come to the Pragma OMP parallel, a number of threads, and the number we can control later on, a number of threads will be created, and they are numbered from 0 and upwards. 0, 1, 2, 3, and so on. And here is the end of the parallel region down here. Okay. When you execute this, this is how it might look if you have 4 threads. Hello 1, hello 0, world 1, world 0, and hello 3, hello 2, world 3, and world 2. Why on earth would you get that weird kind of printout? Well, the reason is that the threads, they get interleaved in unexpected ways. So the printf statement in itself is thread safe. That means that there are synchronization mechanisms inside the library routine printf, so that once a thread has started to execute printf, it will finish and it will not be sort of interrupted. Otherwise, the individual letters of hello and world would become bangled. But you have one printf statement here and another printf statement here, and they, of course, can be interleaved with the different threads in any way. So you have the hello 1 here, and you have the world 1 here, hello 0, world 0, hello 3, world 3, hello 2, and world 2. So the hello 1 always comes first, then the world 1, and so on. But otherwise, you don't know, because there is no synchronization. The threads can execute in whatever order they like. They could be sequentialized on one core, or they could run in parallel on several cores. So how do the threads interact here? We have a multi-threading shared address model. Threads communicate by sharing variables. That's very important to bear in mind. And this communication does not come for free. There is a cost to it. Unintended sharing of data causes race conditions, and it's a good practice to program so that race conditions do not occur. Race conditions happens when the program's outcome may change when the threads are scheduled differently. So we use synchronization to prevent data conflicts to happen. But synchronization is expensive, so what we can do is we can change how data is accessed to minimize the need for synchronization. More about this later. And now it's time to take a break.